Welcome back, Calc. We're going to get into 4.7 and making connections with graphs with the function, its first derivative and second derivative, and we're just going to keep moving on. So just as a heads up is at any point, the AP test could give you any one of these bits of information and ask you to go like back and forth. So you have to pay close attention to I guess how it's phrased. This is the second derivative. So just a reminder, if we have a second derivative, what that means is we have is equal to 0 or is undefined. We have a potential point of inflection. And you may remember why we have to say we have a potential point of inflection is what we could have is the second derivative equal to 0, but maybe it's concave up on the left side and concave up on the right side, so it doesn't actually change concavity. But there's also the connection that we haven't talked about yet between the second derivative and the first derivative. Now, we've talked about the second derivative test, but the only thing that we can really claim from this is at f prime of x, again, we have to be careful here. We have to say it's a potential relative min or max. And the moral of this is understanding that if they give you the second derivative, well, this is the derivative of the derivative. So it's really getting you to understand that the connections that we've established before between a function and its derivative needs to be the same between the first derivative and the second derivative. So to save some time, I'm going to pause the video and get you to think a little bit. And maybe you can try to fill this out, or you can just read through this and see if you can make the connections yourself. And I'm going to actually switch over to the answer key, and then you can hit pause and you can write everything down. So now is the time to hit pause if you want to try this on your own. So as I mentioned, I was going to move right over to the derivative, the answer key, and you can pause the video and write this down and see if your answers match up. So remember, if the second derivative is positive, that means the original function is concave up. It also means that the first derivative is increasing. Make that note between the second derivative and the first derivative, because it's the derivative of the derivative. If the derivative is increasing, then the second derivative is positive. So we already made this first connection between the second derivative being negative, then the original function is concave down. Well, since the second derivative is the derivative of the derivative, that means the first derivative is decreasing. The next one, again, we've already established the first derivative, the original function is a point of inflection if the second derivative changes from positive to negative, but we haven't made this connection yet. We've made the connection between the function and its first derivative, but not between the first derivative and the second derivative. So that means that the first derivative has a relative max, and then this last one down here has a relative min for the same reasons. So if you're confused, write down your question, come to class, or set up a Google Meet, and we can discuss this. I'm going to go back to, well, actually, I think, yeah, I'll go back and work through the next one. Actually, because I don't have my graphing calculator set up, I kind of have to explain it here, as I can't really go back and forth between the derivative. Let's see what I can do. Okay, so decided to just go to Desmos and type this in. We actually only care from -5 to +5. So because this is the graph of the derivative on that problem, even though it's below the x-axis, all that means to me is that the function is decreasing this entire time until I get to x equals 0. And then once I get to x, I think that's exactly 0. Yep. And then as I go to the right, It's increasing because the derivative is positive. So that's exactly what the answer key is saying based on the graph, how many relative extrema. Well, it only crosses the x-axis once. So that means there's one extrema. And we can actually specifically say what kind of extrema it is, because it goes from, H goes from decreasing, so it goes down, to increasing up. So that must be a relative min. Now, based off that, how many points of inflection would it have? Well, a point of inflection, it depends on where the first derivative is a min or a max. So as I go back, starting at -5, I don't care about that one. It's to the left of -5. Crosses right here. You can't really see what the x value is. 1, 2, 3. This is not a min or max, just cross the x-axis. 4, 5. So I counted 5 relative extrema, which is why we have 5 points of inflection. Oops, I can't highlight, I guess. And so this individual walks you through how you can use Graphit on your graphing calculator. And what I can actually do with Desmos, which I didn't do, I think I can just name it as the derivative. Never actually done. Nope, it won't let me. So on Desmos, I just have to leave it. But I can graph the derivative, and you can confirm. Okay, so this is really the second derivative, because it's a derivative of the derivative function. And you can confirm the x values that I mentioned before are points of inflection. See how all of these values are matching up? All the x values, I should say. And you can see why the graph of the derivative would be 0, because that's the slope of the derivative. These are horizontal tangents. Kind of confirm that for you. Go ahead and pause the video and make sure you understand some of this stuff. You might want to practice with a graphing calculator as well, because you don't have Desmos. You don't have access to Desmos on the AP Calculus Day. And I'm actually going to stick with the answer key, because the next page is just filled with what implications every one of these statements is. So I kind of have a preference on how I would write it, but these are good answers. So instead of bouncing back and forth, it makes sense just to go straight to the answer key. And at any point, feel free to pause or rewind and try this on your own and see if you understand. I strongly encourage that. So if you're given a problem where it says that the function is increasing, so I'm looking at here, what does that mean for the derivative? Well, we've talked about it for a while now. That means the derivative is positive. Same thing, just flipping it. If the function is decreasing, that means that the derivative is negative. Well, if we have a relative max or min, that must mean that the derivative changes signs. If we have a point of inflection, then that means, well, remember the point of inflection, you might have to think about this. As a point of inflection means the second derivative is 0. Well, if the second derivative is 0, that means that the first derivative must have a relative max or min. I like to think about it is if the second derivative is 0, that means that the first derivative must be a horizontal tangent. Well, if you have a horizontal tangent, that must mean a max or a min. Sometimes we use the phrase changes increasing to decreasing or decreasing to increasing. So that's where we get into fancier words. All right. So some more connections to make. We've already talked about these next 3. So I'm going to jump to 8. If the first derivative is increasing, that means that the second derivative must be positive. Notice the similarities between number 8 and number 1. Okay. And by the way, we could have taught this like a month ago to you guys. Okay, we just, it gets complicated, so we typically wait until we've gotten a lot of practice with some tougher concepts, and then we come back to it. And then if the first derivative is decreasing, that means that the second derivative is negative. All right, so feel free to pause at any point, really soak this in because we have a lot more to do. You could try the next few on your own, and then I'm going to scroll down. And then you can get the rest of them. So the first derivative has a relative max or min. That means the second derivative must change signs. You might even mention that if the first derivative has a relative max or min, it must be a point of inflection. It must be a point of inflection, which by definition is concavity changes. All right, so moving forward, if the first derivative has a point of inflection, that means that the second derivative has a relative max or min. That's kind of a obnoxious number 11. I don't think they'll ask you to do, but it's worth mentioning. Number 12, if the first derivative changes from negative to positive, that means that the function itself has a relative min. We've talked about that. 13 is the opposite. Number 14, if the first derivative has a relative max or min, then the function has a point of inflection. If the second derivative changes from positive to negative, then the first derivative has a relative max. And then if the second derivative changes from negative to positive, then the first derivative has a relative min. So I'm going to hit pause up here. And what the directions are actually asking you to do, sorry, I'm all over the place, is getting you to recognize that we have 15 graphs. And what we need to do is go through all of them and see which ones match up with the first, second, or which one's the original function for each one. So I'm not going to get scissors and cut things out and share this with you. I'm not even sure if we're going to be in person or not by the time we do this activity. So it just might be something that you have to try on your own. A good thing for people to recognize is typically we don't get higher than like a quartic function. So the higher the degree, the more likely it is to be just the original function. And the reason why I say that is then if I ask you for the derivative, it's going to become a cubic function. And then the second derivative of that, would be a quadratic. And the third derivative of that would just be a linear. And I don't think we've ever gotten to the fourth derivative, but we just put in parentheses. I don't know why. It just becomes a horizontal line. So that's a good clue for you guys. Let me clear that off. Because as I'm looking at number 2, this is a cubic. So definitely is going to be one of the function, like f of x. Number 4 is a cubic as well. You can tell by the end behavior. 6 is a cubic. And it looks like moving past then, there's a lot of linears. Okay, so number 9 is a quartic based off of the number of turning points. You can also tell by the end behavior. Let's see, number 15 looks like a quartic as well. So maybe we should start with one of those. Here's my clue to you. So I'm going to call number 15 f of x real quick. Well, right now I can tell that we have a min or a max. So what I do for the derivative is I think about, okay, well, if the derivative here is 0, right, it's a horizontal tangent, so its derivative must cross the x-axis. Same thing with right here. It's a horizontal tangent, derivative cross the x-axis. Horizontal tangent cross the x-axis. What I do is I think, well, at first it's decreasing, which means the derivative must be negative. And then it's increasing between the min and the max, so this derivative must be positive. Then decreasing, so negative. And then to the right it's increasing, so positive. So that's a quick graph of its derivative. And then I would find what matches, to number 15 on this. But I've run out of time for this first screencast, and I'll need to come back to finish these videos.